So our next speaker is Jason McLain, who's talking about solar wind proton induced hydroxylation on lunar soil 78421.
Hello, everyone. Hopefully you can hear me.
Sounds
I don't
good.
have a camera, so we'll just, but I'm here. And yeah, this study really started, we wanted to understand the rate of this process. So, the solar wind, of course, is mainly protons, and it comes and impacts the lunar soil. And that process then creates hydroxyls, and this paper's in revisions, and I really wanted to thank Casey for helping us interpret some of these IR spectra. So I just wanted to jump on in here. So we had a few null results at first, and this is due to this process of de and rehydroxylation. And Zurlov's model in 2000, which we verified with this study, really made us get a handle on this experiment. And I can just take you through this. I mean, this is fairly simple dehydroxylation model. And so in stage one, when you have like a silica or silicate in vacuum, you just you remove the multi-layers of water, and that's done at room temperature. And then as you start increasing the temperature, you really start to remove all of those water molecules. And at this point, it's interesting because dissociative absorption is barrierless. So the activation energy is zero. So if a water molecule actually comes back down at this time, it'll dissociate and rehydroxylate the surface. And as you continue up in temperature, things change quite a lot. You start making these bridge bonded oxygens and such. And at about 670 Kelvin, now that same process of rehydroxylation with molecular water becomes an activated process. So it requires energy to split the water on the surface, or actually it's not the water, but it's these bonds here that are really strong. If you take that one step further, then what you'll see here is that now it's the surface becomes hydrophobic. So the process is hardly reversible. It's so strongly activated that I took a sample of this silica, which we heated to this, and boiled it in water, and I could not get any IR signature of OH. So at sort of first glance here, we see that we're never going to see protons hydroxylate unless we remove most of the ones that are there. And another thing that was important here was we were not able to do this all in situ. So we had to remove the samples and put them in the spectrometer. So being able to do that without the contamination of the terrestrial water was really important. So here, this critical heating step, we were able to remove most of the water, and then we sort of had time to move the sample around without worrying about terrestrial water rehydroxylating the sample. We put the samples in a ultra high vacuum chamber, and our first results actually came with this fused silica that was just by happenstance, I chose that. I figured it would be the easiest to check. We used olivine at first and other analogs before we went on to the lunar sample. And so here you can see the silica being irradiated with 2 kV protons, or I'm sorry, H2 plus. And I wanted to mention just real quick about, so H2 plus, I mean, we know that's not in the solar wind, and but as many of you might know, for an electron impact ion gun or even a plasma source, you can use a VIN filter, a E cross B filter to filter out the H2 plus, where you get H plus, and we can do that. But the issue is that the H2 plus flux is just orders of magnitude below. I mean, the H plus flux is orders of magnitude below H2 plus, and so, there's been question of whether or not the H2 plus reacts differently, but there's a body of evidence in the literature, and even we have of evidence of this with neutral atoms that show, especially Visor in 2002, ion scattering studies where incident H2 plus, it completely dissociates on a surface. And one interesting thing about this is that, the resulting momentum transfer is essentially a beam of two solar wind sort of type protons. And the mainly the charge fraction is neutral hydrogen, and about 20% is converted to H plus and H minus. Uh, Another interesting thing that you'll find is that this process doesn't even really depend on the initial charge fraction of the ion. So you can have H plus or H minus or H neutrals, and you still get this transfer of about 80% neutrals. So we take the sample then and we put it into a drifts setup inside the spectrometer, and we've actually got a way to heat this sample up as well. So I'll present some of that. So the first results show really nicely. We get this really nice check mark feature, really sharp OH feature on the fused silica. You can see here, I measured the back of the sample, so there's no radiation here. The sample's on the order of a couple millimeters thick, and then as we continue, we can see this start to grow in this really nice OH feature. So now we look at the Apollo sample, and we get quite a different result. And so this is very similar to what Ichimura saw. And for a while there, I was skeptical, but you definitely see that there's a large difference between the Apollo sample band at at 2.7, and then at here it's broad, going all the way to almost 3.8 microns. For those of you that are familiar with these spectra, you know that this is also where the absorbed water band is. So we were kind of struck, like, well, what's going on here? And they simply said, well, this is due to this inhomogeneous broadening. And
8-minute mark.
okay, thank you. And that is very interesting. And so we decided to compare with their results. And here are our results. There's a follow-up spectra taken of the same sample. And you can see here that the overall feature from 3 different samples, Highland calcium plagioclase, and then a high iron, magnesium peroxine, and then our sample are all very similar, which was really really interesting, and maybe we can understand that if you know, with the fact that most of the surface of the minerals on the surface of the moon are silicates, and so you have this silicon tetrahedron backbone where you're forming these, and you're forming them, and they're really being broadened by just being thrown into this very strange mix of defective material. One of the things we were curious is, well, how much water uh, is being absorbed on there during or after the transfer. And we can see here that there's really not much of a 6 micron band to be observed. So we believe that this is all OH, just broadened OH on the real lunar materials.
And then
So
Mark.
we did a temperature excursion and found that if you heat it up in the spectrometer and then let it cool back down to 25 Celsius, you do get a decrease in the band area, about a 20% decrease. So we did remove some. Uh, However, the band shifted. So uh, we have plans to do this all in vacuum now, and really try to understand the equilibrium concentrations. And for the few silica, I have them here in the summary, and for the 7842, which it's about every million hydrogens produce an OH. Thank you.
Thank you so much, Jason. I'm going to go ahead and direct you to the chat box and ask that you stay tuned at the end of the section. But we're going to go ahead and move on to the next speaker.